Hi and welcome to the lecture on power system operation and control. Today we are going to discuss about the economic load dispatch. So what is meant by economic load dispatch and what are the different methods in order to allocate the load to different generating units. Firstly, coming to the objective function of economic load dispatch problem. So, the objective function is to minimize Ci of Pci. So, that is nothing but Ci, cost incurred in generating the power Pci. Ci is nothing but cost incurred to generate power Pgi. Okay, so thermal units have thermal generating stations have different units. So what is the cost incurred in generating a particular unit and amount of power Pg? So Ci is nothing but what is the cost incurred in generating power Pgi and subjected to some equality constraint, subjected to some load balance equation. So this is nothing but a load balance equation and also called as a constraint. That is nothing but an equality constraint where power generated should be equal to power demand plus power losses. So whatever the power that is generated at the generating station, it should be given to the what is the demand is and some amount of power is lost in the terms of losses. So if losses are considered to be 0, if losses are 0, then Pg is equal to Pd. Whatever the power generated is nothing but equal to the power demand. So when the losses will be 0, if the load is at the generating station itself, suppose if the generating station has load near to the generating station, then the power losses will be equal to 0 since there is no transmission system, right? So this is Pg is equal to Pd. So now we are going to discuss only the thermal units. First we will be discussing about the thermal units. Next the combination of thermal and hydro units, right? So now from this, how you can get a best load flow solution? How you can get a best load flow solution? Not only the cost, but we need to see best load flow subjected to some different constraints, right? But the public always needs the cost. But as a power system engineer, we need to check in addition to the cost whether the best load flow solution comes under whether it is subjected to reliability or optimal operation of generation. Next one, operating costs. And again in operating costs we have fuel cost, labor cost, and maintenance cost. So in operating costs we have fuel cost, labor cost and maintenance cost. And in addition to this, we have Best load flow can be subjected to input or by output curve and input energy rate curve, right? So these are the different limitations in addition to the fuel cost minimization. So always not only the cost minimization is our main function. In addition to the cost minimization, we need to check whether the load flow solution or whatever you are getting, it does not have any reliability issue. Whether the generation is optimally allocated or not. We need to check about the operating cost, right? And also we need to check the input output curve, how the relation between the input and output of a particular generating unit is. So we need to check all these conditions in addition to minimizing the cost. So now in the operating cost we have fuel cost, labor cost and the maintenance cost. But mainly the fuel cost is the major part of an operating cost, because the fuel cost will be higher in a thermal power plant. So in addition to that we have some labor cost, or the operators those are maintaining the thermal power station. So those costs are nothing but some labor cost, and also the thermal units might be in maintenance, right? So during that maintenance the generating stations might incur some cost. So these are all the different operating costs in any power station, right? Now let us discuss some basics about the thermal power station. How the fuel input is given and how much amount of power will be produced in a thermal power plant, right? So firstly we will be giving fuel input to a boiler. From the boiler we get steam. So that steam is given to a turbine. So from that turbine we get rotation, that is nothing but mechanical power output from the turbine. So whatever the mechanical power that we have obtained, that is given to an alternator or a generator. To a generator. So from that generator you get the electrical power output, right? But whatever the electrical power output that we have produced, the total power output cannot be given to the load, because some part of power is given to auxiliary power requirement in the power station itself. So some part of power is used by the different equipments in the power station itself. It might be boiler, feed pump, some condensers, there might be some power requirement for electrostatic precipitator. So it might be around the percentage of some 5%. So remaining 95% will be given to the load, right? So this is the general layout of a thermal power station. But in terms of fuel, here what is the fuel input to a thermal power station? The fuel input is coal, right? Whether if you are talking in terms of amount of heat input given to a boiler, right? Then we will be talking it as BTU per hour. That is nothing but British thermal units, right? In terms of heat input. If you are talking the fuel input in terms of heat, then it is British thermal unit per hour. Per hour, how much amount of heat you are giving to a thermal power station, right? If you are talking in terms of amount of fuel, if you are talking in terms of amount of fuel input that you are giving to a boiler, that is how much kilocalories that you are giving per hour, kilocalories per hour, right? So if you are talking in terms of cost of fuel, what is the cost of fuel? Then the input can be rupees per hour. So mainly we will be dealing with this rupees per hour. Per hour, how much amount of cost is being incurred in a particular unit in a thermal power station, right? So if you are talking in terms of heat input, it is British thermal units per hour. If you are talking in terms of amount of fuel, how much tons of fuel is used, kilocalories per hour. If you are talking in terms of cost of fuel, that is simply rupees per hour, right? So now coming to the different system variables in a thermal power station, right? Coming to the system variables. First one is what are the control variables. So what does these control variables will do? These control variables control the operating state of power system network. In which state does the power system network is. So these control variables control the state of the power system network. So those control variables are nothing but PZ and QZ, that is active power generated and reactive power generated, right? So these are the two control variables in a thermal power station, right? So next one, disturbance variables. Disturbance variables. So what these will do? This will continuously alter the state of the power system network. Means these variables try to disturb the power system network. If at all, if the system is in normal state, when these disturbance variables changes, they alter the operating state of the system. So what are these called as? Those are nothing but PD and QD. Similarly, this is active power generation and this is reactive power generation. Whereas these are active power demand and reactive power demand. So disturbance variables are active power demand and the reactive power demand. So these are also called as demand variables, right? So third one is state variables. State variables are nothing but V and delta. Delta is nothing but load angle. V is voltage, delta is load angle. So these two are the state variables in a power system network, right? So these variables are also called as dependent variables. Means these variables depend on PZ and QZ, right? So these variables are dependent on the control variables PG and QG. So these are the different system variables. Control variables: active power generated, reactive power generated. Disturbance variables are active power demand and the reactive power demand. State variables are nothing but voltage and the load angle. Right? So now we are going to discuss the input output relation of an thermal power station. Right? So this is how the input output characteristics of an normal thermal power generator will be. Right? So here you can see the fuel input can be in terms of kilocalories per hour. That is nothing but amount of fuel you are using. BTU per hour, that is British thermal units per hour, means amount of heat input you are giving to a boiler. Similarly, these can be converted into corresponding cost per hour. So that is nothing but fuel cost per hour. That is rupees per hour. So fuel cost is rupees per hour. So in the input output characteristics, you can saw there is some megawatt minimum and megawatt maximum. So these between these megawatt minimum and megawatt maximum, you have the dark lines, and beyond those you have some dotted lines. So what does these reflect? Generally, what does these reflect? So this megawatt minimum represent the minimum amount of power that should be generated, right? If at all you are committing an power, you are turning on a generating unit, whether the power output will be 0. If at all the power output is 0, so what is the possibility or what is the use of turning on a generating unit, right? So there is some minimum amount of power that you need to generate when an alternator is connected in a thermal power station, right? So it is not feasible to generate the power below the minimum megawatt minimum limits, right? If at all the unit is turned on, it should generate minimum amount of power generation, right? Similarly, you have some megawatt maximum, right? So suppose if the alternator is having a capacity of 100 megawatts, right? Means you can continuously generate 100 megawatt power in that particular unit, right? Based on the fuel input, if you are giving a complete total fuel input, you can generate 100 megawatt. But you cannot generate, suppose if you are increasing the fuel input to generate a 500 megawatt plant, can it generate? No. So if at all it generates 500 megawatt, you can call it as a 500 megawatt plant, right? So 500, so the generator can generate only some certain amount of power. Suppose the rating is 100 megawatt maximum. It can generate all the time. It can generate some 110% to 120% for only for some amount of time, right? So based on the design of the alternator, based on the fuel input, can generate only up to maximum amount of power, right? So these are the megawatt minimum and megawatt maximum limits that a alternator can generate in a thermal power station, right? It is not feasible to generate the power below the megawatt minimum, but for some time you can generate the power greater than its maximum limits. That is only for up to 110% or 120% for some amount of time, right? So if you try to write an equation for this curve, you can get it as, you consider fuel input as some F. So then you can write it as F is nothing but AI PGI square plus BI PGI plus CI. So whereas output is PGI and the input is F. Right. So this is a simple curve fitting technique. If you try to write the equation for this curve, that is simply F is equal to AI PGI square plus BI PGI plus CI. Right? That is nothing but it can be fuel cost or a fuel input. Generally we talk in terms of only the fuel cost only. So fuel cost F can be written from this curve as AI PGI square BI PGI plus CI, whereas this AI, BI and PGI, CI are different constant and PGI is nothing but power generated. Okay, this is nothing but a power generated, PGI. Now let us try to know about the incremental fuel cost. Suppose if you are increasing some fuel input by delta F, if there is some increase in the power input, then how much amount of power is increased? How much amount of generated power is increased? That is nothing but for change in the delta F, what is the change in delta PGI? So that is nothing but an incremental fuel cost. Delta F by delta PGI. Otherwise it can be written as dou F by dou PGI. That is incremental fuel cost. Right? So if you derive this one, you get 2AI PGI plus BI. So you consider here it is a second order degree equation. So that's why the incremental fuel cost is a linear equation, right? So if you approximate it to a third order equation, then the incremental fuel cost will be a second order. Right there. So here there is an approximation of this curve as AI PGI square plus BI PGI plus CI, and the incremental fuel cost, that is nothing but for a small input change in fuel, how much amount of power generated is being changed, that is delta F by delta PGI, that is 2AI PGI plus BI. Right? So this is about the incremental fuel cost.